Hey you all! Welcome to my channel Loss Prevention Maverick, which pertinently is intended to provide a little bit of know-how on the various fields of process safety and loss prevention. And today we will be talking about functional safety. Being a rather elaborative topic, I intend to break it down to not less than 7 parts, and today we will be looking into the introduction of it. So part 1. A little bit about me. My name is Rahul Pateri. I've got a master's in process safety and loss prevention, and I'm also a functional safety specialist. I've been fortunate to be 15 years young in the field of process safety and loss prevention, where I started my career as a firefighter involved in active firefighting. So I have fought a few fires in my career. Moved on to EPC companies for both the onshore and the offshore. Then proceeded my career as a risk specialist into doing dispersion calculations and risk assessments. My career took me to as an oil and gas operator, where we rolled out the process safety management, did COMA guidance, incident investigations, and now I am with an onshore refinery and petrochemical complex, exercising authority, having jurisdiction in process safety and loss prevention. So this functional safety series, we would be talking about some safety concepts. We would be looking into introduction to functional safety, certain things like LOPA, safety instrumented systems, SIF, the standard 61508 and 61511, water SIL, that is safety integrity level, and certain salient features of the same. So part 1 of this lecture, we would be talking about these. Further, we would be listening, or rather I would be, I hope and intend to make videos on SIF failure states, certain hazard and risk analysis, hardware design and architecture, software design and architecture, certain compliance routes that these hardware and software are subjected to as part of the standards, and how to manage functional safety. So now let's understand some safety concepts. So starting with personal safety and process safety. So what are the difference in them? Let's see. Personal safety talks about slips and trips and falls, whereas process safety talks about loss of containment, when something, the hazard which is supposed to be inside a pipe called a containment or primary containment, that is outside of its primary containment, is called a loss of containment, and the effects, which could be fire, explosion and toxics. Personal safety talks about workplace hazards, whereas process safety, as the name suggests, is about process hazards. Occupational safety is a part or a subset of personal safety, and here operational integrity, people also have heard about asset integrity, is part and the subset of a process safety. For encouraging or for improving or continually improving, they say, for personal safety, we have to have measures like changing behavior, behavioral management, behavioral based safety is also being said. And for process safety, it's about changing the environment, the conditions. So if you look into the characteristics of personal safety versus process safety, personal safety is something which has a low consequence, but it is very frequent, and the risk receptors are mostly within the workplace itself. If there is lifting and something happens, the consequence would be relatively lower. And the risk receptors are all those which are within the workplace, within the boundaries. Vis-a-vis for a process safety, fortunately it's not so frequent, but the consequence is quite high. Like we've seen, if it's a fire or an explosion, it is not something that will be confined within the workplace, but it can also go to communities. So now to continue, why do we need to differentiate after all? It's all about safety, isn't it? Well, this distinction is important. Why? Because it has to be managed differently. When it comes to personal safety, usually it is something that we've heard about HSE management system, and it's focused on lifting, road cutting, industrial hygiene and health, etc. And the risk assessments are mostly in terms of job safety analysis, permit to work, task risk assessments, etc. Whereas for process safety, it's called a process safety management. And the skills mostly looked into are ISD, which is inherent safe design, HAZOP, LOPA, that's layer of protection analysis, consequence modeling, etc. The risk assessments here are termed as QRA, FRA, emergency evacuation risk assessment, EERA, etc. Well, process safety and personal safety has certain common factors. For example, both of them need effective leadership. They all depends upon the culture that the organization portrays. There are incident investigations for both of these. Everything has certain measurements, certain KPIs, certain metrics to continually improve and look forward to. And there is verification and audit for both these personal safety and process safety. Now, having had a flavor on the basics about personal safety and process safety, now we come up to a hot topic. What is functional safety? So in accordance to IEC 61511, which is the standard for functional safety for safety instrument and systems and process industry. So the definition here is part of the overall safety relating to the process and the BPCS, which depends on the correct functioning of the SIS and the other protection layers. Honestly, reading that, I didn't understand anything. But then I came across to Dr. Michael Houtmans of Risknology in his book called SIL in a Nutshell, where he defines functional safety which is a property of an active safety function carried out by a safety system. An active safety function detects some kind of undesired situation and then takes action. So what we have understood here is functional safety is a science, or it's a property wherein some sort of a safety function is carried out by the safety system. So what it does is it averts some undesired situation. So in order to avert an undesired situation, a system takes in some kind of function or an active safety function, and this particular science or the property is called functional safety. Well, let's see here with an example. What is the undesired situation or something that we commonly or very frequently come across on the streets? And that is yes, indeed. So the undesired situation that we come across are accidents and loss of life because of the impact of these accidents. So here, what is the active safety function? The active safety function here is that as soon as the instrumentation or the microprocessor, the chip inside the car understands or it gets a signal of the sudden deceleration, the airbag pops up. So what is the active safety function? The active safety function is such that the airbag pops up, and what does it avert? It averts a potential fatality of the person on the wheel and the passengers. So here, if we really look into the concept of process safety, I will have to come to this conclusion that functional safety is also a subset of process safety. So we've seen personal safety and process safety. There are certain common factors between the personal safety and process safety, and functional safety is in fact a subset of process safety. Having seen personal safety, process safety, and also having understood that functional safety is a subset of process safety, now let's look into something called as layers of protection, or like we previously seen, layers of protection analysis, or LOPA. Every process system or every system has certain or various layers embedded into the system or into the process to ensure that the hazards such that remains in the containment or remains inside the pipes, or now in the uneventful scenario that it comes out, so-called loss of containment, the risk from the hazard is mitigated or is not escalated such that the risk is in a LARP as low as reasonably practicable. So to start with, the first layer of protection is called inherent safe design or inherent safe plant design. So it looks into a lot of inherent safe design practices. Let's say the design philosophy is such that all the vessels and the piping and the related flanges and every equipment in the process is designed for the maximum pressure that the system can see. For upstream, that is in wells, we can say that it is designed for well shut-in head, and for a pumping process, let's say it is designed for the pump shut-off head. So that is an inherent safe design feature. And now talking about inherent safe design feature, also locating the process plant is also something of an inherent safe in nature. If we keep a process plant bang close to a community, yes, we could have risks of the scale of Bhopal, or now very recently of the styrene incident in India. But vis-a-vis, if these process plants are now far away from community, far away from schools and townships and all that, the risk to community can be less, or it can be minimized. So that is called a inherent safe plant design layer, barrier. The next layer is called BPCS or DCS, so called. BPCS is basic process control systems. So what is it? The hint is in the name itself. These are control systems. So these are instrumented systems which help in controlling the process variables. So what are the process variables that we normally look into? It can be flow level, pressure and temperature. So those instrumented systems which ensures that the process variables are under control. So that is called a basic process control systems or a distributed control system, the DCS. Now let's look into an event wherein you are filling up your tank. So the tank is being filled, and then the level now goes to a high level. So when that happens, teet, 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 yes, the alarm goes alarm goes off, and the operator is now cautioned, and the operator has to execute some sort of an action in accordance to the SOPs and his training. But then humans, yes, there's a lot of factors. It looks into what is his emotional state of mind at that particular time, how many alarms are there, what is the level of training, what is the level of fatigue. So this particular barrier can fail as well. So once that barrier fails and this level now goes from high to a high level, the next barrier, and that is called a SIS or a safety instrumented system. So what is a safety instrumented system? A safety instrumented system is involved to ensure that there is some kind of an active safety function in it to avert an undesired situation. So what is the undesired situation over here? Is that is an overfill which could probably lead to a Bunzfield incident. So in order to avoid that, the safety instrumented function averts by shutting off the pump. It trips the pump, and therefore an overfill incident is averted. So how is a safety instrumented function different from a process control system or a BPCS? Yes, the difference here is that basic process control system is a controlling function. It can control against the various variables, whereas safety instrument system is an executable function. It executes something, an on-off. So when an undesired situation is observed or identified, it shuts down the process or it starts a process, it blows down the system, it ventilates the atmosphere, example. So these barriers are therefore called as prevention layers. And why are they called prevention layers? Why? Because if these barriers are intact, the hazard is still in the pipes. Now let's say that the safety instrumented system does not work, and when that happens, let's say the pressure in it goes up and it gets relieved from a pressure relief device, a burst disc or something like that. So in that case, what happens now, those hazard or that hazard which is supposed to be inside the containment is now released outside. So as it gets released, the next level of barrier is a passive barrier, for example a dike. So what happens if a dike reduces the spill of the fluid, and as it reduces, what it effectively does is it reduces the surface area, less surface area and therefore less evaporation and less flashing and less flashing fraction of the flammable fluid. For the next level of barrier is a fire and gas and active fire protection. So as soon as something goes on a loss of containment, when there is loss of containment, the effectiveness of the detection is very important. And once detected, according to the cause and effect, probably it will go to start your fire water pump, and then there will have some sort of a active fire protection system in place, like energizing the deluge system, or maybe a foam deluge system, maybe some monitors has been activated, etc. Then once it also goes outside, the hazard sort of overshoots the active fire protection, then the plant emergency response plan kicks in. You call up the fire service department if you have one, the fire trucks and the mobile units come rushing in, you have mutual aid people come in, and then they try to sort of mitigate this particular event, and therefore it's called a mitigation layer. So here in this layers of protection, we have seen prevention layers and mitigation layers. Prevention layers are those layers which ensures that the hazard is within the containment, and mitigation layers come into play or are activated once there is a loss of containment, and these barriers ensures, or it's a property of these barriers to ensure that the escalation is mitigated as soon as possible with the lowest risk potential. Now we've seen LOPA, and we have addressed that of the various protection layers, SIS, or the safety instrument system, is one of them. So here we see safety instrumented systems have been used many years to perform safety instrumented functions. Yes, makes sense. But now let's look at them individually. Safety instrumented system and safety instrumented function. So safety instrumented system, IEC 61511 defines safety instrumented system used to implement one or more safety instrumented functions. So here please take note, it is used to implement one or more safety instrumented functions. Okay. A safety instrumented system is a combination of sensors, logic solvers, and final elements that performs one or more safety instrumented functions. So therefore here we come to know that a safety instrumented system is a combination of sensors and logic solvers and final elements which performs one or more safety instrumented functions. A safety instrumented system, yes, always need to start with an instrument. An instrument over here is a jargon used to indicates something or anything that can be adjusted, handled, or controlled. So a safety instrumented system, it is used to implement one or more safety instrumented functions, is a combination of sensors, logic solvers, and final elements, and it always has to start with an instrument. So that is a safety instrumented system. Whereas what is a safety instrumented function? IEC 61511 comes to our help. It says a safety function to be implemented by safety instrumented system. I mean, this definition is kind of an indirect association over here. For example, where's your house? Oh, mine is next to John's. And where's John's? Oh, next to you. So this kind of definition really doesn't give so much away. So I looked into some other literature where it was said a safety instrumented function, a definition was a specific single set of actions and the corresponding equipment needed to identify a single hazard and act to bring a system to a safe state. So here we need to look into a specific single set and corresponding equipment. So which means it is a safety instrumented function is the equipment which has the action to avert an undesired situation. So a safety instrumented function is in fact a sensor, a logic solver, and a final element, all individual single ones which have a defined action. So here, yes, the thing that has to be highlighted is SIF is a specific single equipment for a single hazard, whereas SIS is a combination of the various SIFs, and SIS has to start with an instrument. So a SIF is also called here as a loop, and a loop means the equipment which involves a sensor, a logic solver, and a final element. So this is what a SIF is, and a combination of SIFs make a SIS. So having seen a SIS and what is a SIF, let's look into the schematics on how a SIS, a safety instrumented system, functions. So what we said, a safety instrumented system has to start with an instrument. So over here, let's bring a pressure transmitter on 1 out of 1 pressure transmitter. It has its logic solver. So pressure transmitter is the sensor. It has a logic solver, and it also has a final element, and it is connected by a pneumatic signal. And now let's look into two other pressure transmitters which have its own logic solvers, and here it is executing a function to close two control or two shut-off valves. And now we've seen that one pressure transmitter over here is sending a signal to one logic solver, and the next one is giving a signal to the next, and both of them are giving actions to shut off the valves. And here we see that these are hydraulic symbols. They are connected by hydraulic linkage. Now we get three other pressure transmitters with its own logic solvers, and again another two shut-off valves. But here these pressure transmitters over here, it was about they were pneumatically linked, hydraulically linked, but here it's all about electronics. So these are all electronic connections. Each of these pressure transmitters give signals to the logic solvers, and those are inherent, and those are logic solvers have a logic on particular predefined conditions to shut off the valves. So over here, by the definition that we've seen earlier, each of these are called SIFs. safety instrumented function, because there's always a confusion in the field of functional safety or between functional safety practitioners or HSE people about what is a SIF and what is an SIS. So over here, each of these particular loop, that is one sensor, a logic solver, and the final element, has its own safety function, and this is called a SIF. And this is another set of series, and this is also called a safety instrumented function, and this is another safety instrumented function. And now the combination of all these safety instrumented function brings what? Yes, I guess all of you have guessed it well. It is a safety instrumented system. Now we come back to the SIS and the SIF definition, and my apologies for harping on to this particular definition of SIF and SIS, because it's very important that we understand and we start to distinguish between SIS and SIF. So what we've seen, a SIF has a specific single set, and it is as a loop which concerns of a sensor, a logic solver, and a final element, which has a function to avert a single hazard. And a combination of SIF is a SIS, and the SIS has to start with an instrument. Now, how many of us have heard about this word called safety integrity level? Yes, most of us have. It's called SIL. So now a SIL, should that be for a SIS or will that be for a SIF? A SIL is in fact for a SIF. A SIL is for a safety instrumented function. Now, having really understood what a SIF is and a SIF is, and having briefly seen that a SIL applies to, not a SIL, SIL, safety integrity level, applies to SIF, we will look into the two important standards that defines the safety integrity level. The first one is IEC 61511, or its alternative, or it's an equivalent American version, ANSI or an ISA 840001. So the title is Functional Safety for Safety Instrumented System for Process Industry. So what do we see here? It is a standard that applies to process industry. So by definition, it means it does not apply for manufacturing and for automobiles and all that other industries. And what have we seen about the safety instrumented system over here? It has to begin with an instrument. So therefore, this particular standard IEC 61511 is not for burst plate, PSVs, dikes, etc. So this standard is used by end users, EPCs and engineering companies. Oh no, it cannot be used by a product developer or a manufacturer. So the IEC 61511 over here, in its life cycle, is used by end users, EPC companies and system integrators, and it cannot be used by product developers and manufacturers. Why? Because it's a loop standard and not a device specific standard. So which means, what does a loop standard means? Which means it comes into play once the sensor, the logic solver and the final element is manufactured properly and is put into configuration. And therefore it is not a device standard but a loop standard. And as we all know, a safety instrumented system starts with an instrument and it is independent. Yes, this is something to be seen. It's independent of the technology of the loop. Earlier in our presentation, we saw the architecture of SIS, architecture of safety instrumented system, where we saw three different safety instrumented functions over there. One was on pneumatic, other one was hydraulic, and the third one was electronic. So it's independent. The IEC 61511 is independent of the technology of the loop as long as it starts with an instrument, and it is a loop standard and not a device standard. Okay, so in that case, now we need to have a standard for product developers and manufacturers, is it not? So, and that standard is called IEC 61508. And what is the title? Functional Safety of Electrical, Electronic, Programmable Electronic Safety Related System. So over here, what do we see? There is no industry mentioned here, and it is called a safety related system, not a safety instrumented system. So which means it can define any loop. Why? Because here a safety instrumented system should have an instrument, whereas a safety related system can be in anything. It can be even a push button to start with. So that particular safety related system applies to IEC 61508 as long as the loop somewhere should contain electrical, electronic or programmable electronic. So this particular standard IEC 61508 is very famously in the process industry called as a product developer standard, and it defines the requirements for making hardware and software. So if the question is asked, IEC 61508 is only a product developer standard? Well, no. IEC 61508, to be honest, is the mother of all beg your pardon, is the mother of all functional safety standards, and it applies in its life cycle to end users, EPCs and engineering companies, product developers, manufacturers and system integrators. The only thing is that in the process industry, we use IEC 61511 just for its comprehensivity, and for making the loop, IEC 61511 speaks to 61508 for developing the products, and once the products are developed, it makes into a loop, and that begins a SIF. And certain examples of SIF here are ESD, an emergency shutdown, HIPS, a high integrity pressure protection system, and a burner management system. Let's come into the distinguishing features or the differences between IEC 61511 and IEC 61508, where earlier we saw IEC 61511 is a process industry specific standard and 61508 is a safety related system standard. So 61511 here has three parts. Part 1, it's called framework, definitions and system hardware and software requirements. Part 2, guidelines for application of 61511 part 1. Part 3 is guidance on the determination of SIN. Whereas 61508 has 7 parts. Here part 1 is general requirements. Part 2 is hardware requirements. Part 3 is software requirements. So part 2 and part 3, when multiply, we get part 6. So part 6 are guidelines for using part 2 and part 3. So here we see abbreviations, hardware and software. So we need to have a part for definitions and abbreviations. Part 5 is example of methods for SIL determination, and part 7 overview of techniques and measures. So now when we write a scope of work and we are into contractual terms with an EPC contractor or system integrator or anybody in the life cycle, and when we say that the person or the third party has to abide by IEC 61511, it means the person is only obliged to follow part 1. Likewise, for 61508, he is obliged, or he or she, or the third party person is only obliged to follow up to part 4 unless and until specified. IEC 61508 is also called as an umbrella standard. Why? Because it defines the requirements for safety related systems in the process industry. It can be in the nuclear power industry, it could be automobile and automotive industry, also for application based functions for gas detection. So Having 61508, 61511 is specific for the process industry, and it is also in 61511 when we need to have an architecture or a loop or a safety instrumented function having a SIL4 requirement. 61511 refers to 61508. This is for everyone's understanding. And it is also to mention that 61511 doesn't stand alone. It is working very closely, or it has various chapters on, I don't say chapters, I'm sorry, it has various connections or links to 61508, not only with respect to developing a product, developing the hardware or writing the software, but also if the need or the demand calls for SIL4, 6151 has to follow the compliance route of 61508. Moving on to SIL, and as we see, it's a safety integrity level. A little bit of segue here. It's when I was in one of the campus interviews, the interviewer asked me, what is SIL? So instead of safety integrity, I said structural integrity level. I still remember that. And this was a time when dimensional accident loading and all that were not very prevalent or not very known, around maybe 16 or 17 years back. That's the case. A little bit of reminiscence. Well, now moving on to our lecture. SIL, as we see here, it determines the performance of SIFs carried out by safety instrumented systems. So here what it means, SIL determines the performance of the function carried out by the system. So it is some kind of a performance marker. So it's a function of the performance of SIF. SIL usually gives the layer of protection or the level of protection, and how much should be the level of protection, how well should be the performance of these SIFs is identified from hazard and risk analysis. So what it does is, once you identify the hazard and you assess the risk and the analysis of the risk, that is how bad it is. So from how bad it is, we understand what is the tolerable risk. So from how bad to how good needs some sort of a risk reduction potential. So that risk reduction potential moves to something called as a SIL. We will learn about all this when I make a video, and then we share on the topic of hazard and risk analysis. So till then, let's see SIL. In accordance to the standard IEC 61511, there are 4 SIL levels, as we just saw earlier, where we said that IEC 61508 is a umbrella standard, and IEC 61511, when we need to design a loop for SIL4, 61511 looks at 61508 for the compliance route. So 61511 has 4 SIL levels. So certain salient features of safety integrity level. As we seen before, SIL is for a SIF. SIL is for a safety instrumented function and not for the SIS. Its SIL is for safety instrumented function. So safety SIL defines the performance of the whole loop, and we've seen loop means the sensor, logic solver, final element, or it can also be a SIF. So these are all synonyms. SIF, loop, all are synonyms, and SIL defines the performance of the SIF or the loop. And when we talk about SIL, when we talk about how much should be the performance of the level of protection, there are nearly 1,000 requirements to be executed throughout the life cycle of SIF which means from the drawing board, that is from writing of the specifications to design, to its configuration, validation, FAT, SAT, commissioning, operating the plant, and even decommissioning. So there are around 1,000 requirements for SIL, of which nearly 90% of these are addressed by the manufacturer or product development via IEC 61508. So nearly 900 of them is at a development level. So these particular requirements, they can include technical as well as non-technical. Non-technical, for example, we need to employ competent people into designing the product. There should be a functional safety management. The particular work needs to be verified, and once it's in operation, the safety instrumented function need to be audited. Likewise, so there are some non-technical requirements for SIL, and there are some technical requirements for SIL, and it's like a particular way of configuring the particular safety instrumented function. Things like HFT, it's called hardware fault tolerance, voting systems, and maybe level of diagnostics. So all this we will learn in other lecture series. So for now, let's understand that SIL, or these 1,000 requirements, have technical and non-technical basis. So from here we understand, higher the SIL, better is the safety function. Yes, higher the SIL level, better is the safety function, and therefore better is the safety availability. So now, safety availability does not mean plant availability, which means that higher the SIL is not a measurement to how much your plant is available. Higher the SIL means how much safe your function is. So which can also be termed as, there could be more spurious trips. So trips which could make the plant to a safe state without actually having an undesired event. But then there are ways on how we can improve the plant availability by maintaining the SIL. These we will see in other lectures. So we saw what SIL is. SIL is a safety integrity level, and we've just seen that there are nearly 1,000 requirements for SIL. But of these 1,000 requirements, the most popular one is, it is called PFD average. Now, just to sort of give an example on PFD and to talk about it, let's take a function over here, and that is about a person applying brake in an automobile, in a vehicle. So just for the time being, just now let's forget that we are in the 61511 industry. Now let's look into 61508, so that there is no need for an instrument. It just has to be a safety related system, and somewhere in the loop we need an electric, electronic, or a programmable electronic system. So here, as the brake is applied, there is some sort of a microprocessor which sort of slows down the vehicle and comes to a random halt. And why is it needed? So that we do not go to an undesired event. What is an undesired event? Yes, there we have it. So now when we say PFD is equal to 1 by 10 or 10 raised to minus 1. So here PFD means probability of failure on demand. So when we say that my braking function has a probability of failure on demand of 10 raised to minus 1 or 1 by 10, which means on 10 demands, it can fail once. So on 10 demands, when I press 10 times, it's okay, but on the 11th time, it could fail. So it says probability of failure on demand is 1 by 10 or 10 raised to minus 1. But now, just to make things a little bit safer, we say now that my probability and failure of demand, or the PFD, looking into the accident potential, fatality and all that, I have decreased the PFD to 10 raised to minus 4. So here, in order to have one failure, I need to have at least 10,000 demands. So just to say, if our probability and failure demand is 10 raised to minus 1 or 1 by 10, to have one failure, we need only 10 demands, whereas when it is 10 raised to minus 4, to have the same one failure we need to have 10,000 demands. So what do we know from here? As the PFD lowers, our safety function is improving. So having understood so much, let's go back to the table SIL PFD average. So what is PFD average? Probability of failure on demand average. So why is it called average? It's a very good question, but let's halt it for now. It will come up as part of our other lectures where we will be talking about hardware requirements. So we have seen that SIL, there are 4 levels of SIL: 1, 2, 3 and 4. And of the 1000 SIL requirements, the most popular one we see is probability of failure on demand average. So for a SIL level of 1, the PFD is less than 10 raised to minus 1 but greater than 10 raised to minus 2. And likewise for SIL 2, SIL 3 and SIL 4. So here we've seen that as the safety integrity level, as the SIL level increases from 1 to 4, the probability of failure on demand decreases from 10 raised to minus 1 up to 10 raised to minus 5. So what is over here? It's RRF. RRF is called a risk reduction factor. And risk reduction factor is the inverse of probability and failure on demand. It's actually probability and failure on demand average. So over here, 10 raised to minus 1 inverse becomes 10 raised to 1. 10 raised to minus 2 inverse becomes 10 raised to minus 2. So a SIL of 1 means it gives a risk reduction factor in between 10 raised to 1 to 10 raised to 2. And likewise for all the other SIL. So here we can see that as the SIL level improves, the risk reduction factor improves. And when the risk reduction factor improves, the probability of failure on demand average decreases because it's an inverse function. So, but sometimes in some literature I have seen that people do not like in terms of probability on failure on demand. Instead of that, they talk about safety availability. So safety availability, it just means 1 minus probability on failure on demand average. It's just various other notions or various other ways of presenting the integrity of the SIF. So here SIL is for a SIF. It has 4 levels. It can be determined. One of the SIL requirements and the most popular one is probability and failure on demand average. As the SIL level increases, PFD level decreases, and when the PFD level decreases, the risk reduction factor increases. And yes, now we come to the end of part 1 of the lecture on functional safety. I would like to give credits especially to the course that I've just completed from Risknology, and the course was presented by Dr. Michael Houtmans, whom I have referred in various instances of this lecture. For people who would like to have a good concrete know-how on functional safety and its importance in process safety and industry, I would recommend to touch base with Rosnology and Dr. Michael Houtemans, and then speak to the person so that you can engage on one sort of a course with him and improve your path of learning on functional safety. And apart from that, I looked into IEC 615-11508, another book called the Safety Instrumented System Design Techniques and Design Verification. That is an ISA publication, and a Practical Cell Target Selection, which is an XCDA publication. Here on the why, I read Simon Sinek's, motivational speaker, his book on the Golden Circle, where he talks about the why, how, and what. So people had asked me about what motivates me, or what is my intent to bring out these series on my video or my channel on loss prevention Maverick. So my why for presenting these videos is nothing but to democratize learning basics and know-how on process safety and loss prevention concepts to start with. Because according to me, learning is a birthright. Things should be free and it should be easily accessible and comprehensible. Now how am I going to materialize my why? Is by taking time from my curriculum, or from my office time and from family time, to learn and bring out the some videos of appreciable quality and comprehensiveness, so that such HSE aspirants or enthusiasts can look at it, view it, and then at least take away some of the concepts. So what do I intend? No, it's not about share, like, and subscribe to the channel and all that. That's not my cause. My cause is that there has been many people more proficient than I am, much more experienced than I, to please follow my why, or follow the why, or follow this infinite game of bringing out more videos and lectures tailored for a range of people, that is from a student to an industry aspirant, on various lectures on various topics on process safety and loss prevention, so that it is available for free. And I would like more people like me to make more videos so that learning can be fun and interesting. As part of Loss Prevention Maverick, this particular series, I have an ideology, and that is to pay tribute to people who have influenced me in my personal, professional, and in my career. And I would like to pay tribute of this particular part 1 functional safety to Dr. G. Madhu. He was our head of department. For SOE is called School of Engineering in QSAT. QSAT is Cochin University of Science and Technology, where I did my undergraduation in safety and fire engineering. Dr. G. Madhu, he is an industry stalwart, and I find his way of teaching, where I say the 3 I's, the trifactor, the 3 I's. So his learning was interesting, it was illustrative, and very instructive. And thank you very much to Professor G. Madhu for aspiring us to ensure that the processes are made relatively safer and people coming to work go back home safely, back to their families, and are happy. Thank you very much, everybody, and please stay tuned for next parts of the series on functional safety. Till then, please stay safe, stay strong, and be happy. Thank you very much, and have fun, everybody. Bye-bye.